When most of us picture chemistry, we tend to imagine these perfectly clear liquids in pristine glass beakers, or maybe perfectly uniform snow-white powders. But the reality? Well, it's a lot messier. When a compound is actually synthesized in a lab or isolated from a natural source like a plant leaf, it's almost always this sludgy, tar-like mess. It's totally impure, filled with unreacted materials, leftover solvents, and just a bunch of unwanted byproducts. Welcome to this explainer, where we're going to shatter that Hollywood illusion and look at the actual reality of the lab bench. So it begs the question, how exactly do chemists isolate pure compounds from such a messy world? That is the core problem we're solving today. We're going to open up the chemist's toolkit and check out the specific, highly technical benchtop methods they use to turn a crude, messy mixture into a pristine, isolated chemical. Here's our roadmap for today. First, the purity problem. Second, purifying solids via recrystallization. Third, identifying solids by melting points. Fourth, separating liquids via fractional distillation. And finally, steam distillation for immiscible liquids. Let's get right into it. All right, part 1, dealing with solids. Okay, let's dive into this. The techniques we're talking about here are literally foundational to almost every organic chemistry lab on the planet. The bread and butter for purifying an impure solid is an elegant physical process called recrystallization, and it relies on a very specific, carefully timed sequence. First up, we dissolve our messy compound in the absolute minimum amount of boiling hot solvent. Second, we filter out any insoluble impurities while that mixture is still piping hot. Third, and hey, this is an absolutely critical distinction, we let the saturated solution cool slowly. Why slowly? Well, crystallization is the gradual formation of a crystal lattice. If we rush it, shake it, or cool it down too fast, we get precipitation. And precipitation just traps all those impurities right back inside the rapidly formed solid. Slow cooling creates a dynamic equilibrium, allowing molecules that don't belong in the crystal lattice to safely return to the solution. Finally, we isolate our beautiful, pure compound using vacuum filtration. Walking through the actual benchtop reality of that process, there are a few key things to notice. Think about that hot filtration step. We use fluted filter paper and a stemless funnel, and they have to be kept hot to prevent premature crystallization on the filter paper itself. From there, the liquid cools in the flask, forming our pure crystals. Then, down at the end of the process, we use what's called a Buchner funnel connected to an aspirator for the vacuum filtration. This isolates the purified crystals from a leftover liquid, which, kind of funny, chemists call the mother liquor, and it lets those crystals dry significantly faster than standard gravity filtration ever could. But honestly, none of this beautiful crystallization happens without the perfect solvent. And the criteria an ideal solvent needs to meet are actually incredibly strict. First off, it absolutely cannot react with the compound you're trying to purify. It needs to dissolve a huge amount of the compound when boiling hot, but practically nothing at room temperature. For the impurities, it's the exact opposite. They need to be either completely soluble, so they stay behind in the liquid during crystallization, or highly insoluble, so you can just filter them out while it's hot. Finally, it should be moderately volatile, so your final crystals dry easily. Finding this unicorn solvent often takes a lot of trial and error, relying on the classic like dissolves like rule. And if you ask any tired grad student, that can literally mean a highly frustrating afternoon of testing vials until you finally find the magic liquid that works. So, you've got your beautifully dry crystals. How do you actually prove they're pure? We test their melting temperature. Now, despite everyone using the phrase melting point, it is really difficult to nail down an exact single number because melting is a thermodynamic process. When a substance starts to melt, a dynamic equilibrium is established. It literally exists in both solid and liquid forms at the exact same time. Because of this energy transfer, we don't usually report a single rigid temperature. We report a range, typically about a 2 to 3 degrees Celsius window. Now, what's really fascinating is how we can use this melting range as an identification tool. It's called the mix melting point method. Imagine you have a purified solid that melts right at 99 to 100 degrees, and you strongly suspect it's compound A, which also happens to melt at 99 to 100 degrees. To prove it for sure, you grind up a 50-50 mixture of your unknown compound and known compound A. If they're identical, the melting point range stays exactly the same. But if they're actually different compounds, those mixed impurities are going to disrupt the crystal lattice. The resulting melting point of the mixture will suddenly be much lower and broader, say down to 90 to 97 degrees. It's just a beautifully simple, undeniable physical proof of identity. All right, shifting gears entirely. Part 2, dealing with liquids. Moving from solids to liquids, what happens when our desired product is a messy liquid mixture? Well, when liquids have drastically different vapor pressures and boiling points, a simple distillation works just fine. But when their boiling points are uncomfortably close together, that's when we need fractional distillation. The entire core concept here revolves around the theoretical plate. As vapor travels up a fractionating column, it condenses and evaporates over and over again. Every single one of these cycles is considered a theoretical plate. Basically, the more theoretical plates you have in your column, the better separation you get between the compounds. In this kind of setup, sitting vertically between the heating flask and the condenser, you have the fractionating column. It's essentially a long glass tube packed with materials, like little glass or ceramic beads. And these beads, they are the real MVPs here, providing the physical surface area needed for those theoretical plates to actually happen. The vapor climbs, hits a bead, condenses, heats back up, vaporizes again, and climbs even higher. This setup allows multiple simple distillations to happen in just a single pass, and that is exactly how we separate miscible liquids with super similar boiling points, like ethyl acetate and butyl acetate. If you were to map the temperature of the distilling vapor against the volume of the distillate you're collecting, you'd really see the gap between theory and practice. In an ideal world, the lower boiling component distills completely at a perfectly constant temperature, and then, boom, the temperature jumps up immediately to distill the higher boiling component. That's the ideal. But the empirical reality of many benchtop setups is usually a more blurred transition. The big takeaway here? By carefully controlling your heating temperature and using a column packed with optimal surface area, you can maximize those theoretical plates and force that messy empirical curve to look incredibly close to the perfect, ideal distillation. But how does all of this math change when liquids just flat out refuse to mix? We just looked at miscible liquids, where the total vapor pressure is the sum of their partial vapor pressures, based on mole fractions. But what if the liquids are completely immiscible, like oil and water? In that case, they do not share partial pressures at all. The total pressure of the mixture is simply the sum of their pure, individual vapor pressures. And this little mathematical quirk leads to a real game changer of a technique called steam distillation. Because the vapor pressures are strictly additive here, the mixture will reach atmospheric pressure, and therefore boil, at a temperature strictly lower than the boiling point of either individual component. Seeing this math actually play out is incredible. To put it into perspective, water boils at 100 degrees Celsius, right? And an organic compound like bromobenzene boils way up at 155 degrees Celsius. But because they are totally immiscible, their combined vapor pressures hit the atmospheric threshold of 760 torr at just 95 degrees Celsius. By co-distilling with steam, we can isolate these really stubborn high-boiling organics at a temperature considerably below their actual boiling point, which completely saves delicate compounds from thermal destruction. We've covered a ton of ground in this explainer, from coaxing pristine crystals out of a sludgy hot solution to vaporizing heavy organic liquids at impossibly low temperatures using steam. But why does this actually matter outside the lab? Well, every time you take a safely synthesized medication that's free of toxic byproducts, every time you use a perfume extracted perfectly from a delicate botanical, or even fill your car with fractionalized fuel, you are relying entirely on the principles in this chemist's toolkit. Without these exact techniques, we'd literally just be stuck with the messy world we started with. Which kind of leaves us with one final thought. As our synthetic molecules become unimaginably complex, will these centuries-old purification techniques still hold up, or are we on the verge of a brand new era of separation science? Thanks for joining this explainer, and we'll catch you next time.